sabe con el forma de conectarme por cosa. No, pero serio, seríamos, no llegamos, seríamos,
خدموا هذا خدموا أجل Test. silencio.
Sí, sí, no. Ya estamos. A partir de mañana.
d'accueillir et de vous présenter notre ami ce papier de l'Université de Lille. Ce talbi est très connu de l'optimisation et particulièrement pour tout ce qui concerne les métaheuristiques. Comme vous le savez probablement, il est auteur d'abord du livre, du célèbre livre, métaheuristique, donc design sur implémentation, et auteur de 8 livres, ou éditeur, auteur ou éditeur d'autres 8 livres. Il est auteur de plus que 200 articles dans des revues internationaux. Peut-être la moyenne par année de ces dernières années, c'est plus qu'une vingtaine d'articles par année. Donc, pour dire plus, peut-être que je voulais inviter son complice, notre ami Rachid, pour dire plus, mais il a refusé. Donc, je vous laisse avec tous ces papiers.
Okay, so thanks for the organizers of the conference, for the invitation, and special thanks for Belafia, the School of Energy. So in this keynote, I will try to give you, to bridge the gap between the area of metaheuristics and machine learning. So I will try first to talk about how machine learning can help metaheuristics to design more efficient optimization algorithms. And then the second part of the talk is how metaheuristics can help to solve better machine learning algorithms. So this is the gap between the two areas, and then I will conclude the talk. So in the first part, I will try to give you what are the main search components in metaheuristics that can be, where machine learning can be used, okay? So I will first talk about the objective function for the search operators, the initial solutions, the parameter tuning, because as you know in metaheuristics there are a lot of parameters. Even in machine learning there are a lot of parameters. We will talk about the hyperparameters optimization in machine learning. And then how to analyze the landscape of the problem, how to decompose the problem, and machine learning tool can help us to make some decomposition of the problem. And then we will switch to how metaheuristics can help to solve better machine learning techniques. So this is the view of, let's say, optimization researcher. So I will try to give you some insight about different problems, clustering, classifications, association rules, filter selection. And one of the main, I think, tasks will be the hyperparameter optimization. As you know, in machine learning, there are a lot of parameters in different models, so how to find the best parameters for those models. Okay, and as you see in this Google plot, there are very, very few words. This is the green plot, bridging the gap between machine learning and metaheuristics. So a lot of things to do in the future. Good. So let's first start with machine learning, how machine learning can help to design better metaheuristics. So most of the metaheuristics, if you take any metaheuristics, we don't use in the method the knowledge about the search. So the idea is how to extract knowledge from the search to help metaheuristics to solve better the problem. So this is the idea. So the first question is, what are the data here? So the data can be static data from the problem structure, from the instance features of the problem. So those are static data. But it can be also dynamic data. We will, from the data generated by the methods, like the search space, the solution, in the decision space, in the objective space, the moves, the neighborhoods, the combination, the local optima that we are generating, the elite solution, the best found solution, how we will extract knowledge from the data generated by the metaheuristics to help, to guide better the metaheristic search. So this is the idea. What are the knowledge that we can extract from those data to enhance metaheuristics by machine learning? And as I told you, there are very few works in this area, so a lot of things to do in the future. And don't forget something, that what is the main objective? Our main objective is always to equilibrate the exploration and the exploitation, to have improve the quality of solution, to improve the search time and the robustness of the search. So those are the objectives. So just very few quick presentation of optimizations. So of course we are dealing here with metaheuristics. I like this classification: single solution based metaheuristics like taboo search, local search, and population based metaheuristics like swarm optimization or scatter search. So in this, my talk, I will deal with this kind of algorithms. Good. So quick presentation of single solution based metaheuristics. They are based on the improvement of single solution. So the idea is to start from the initial solution to generate a given neighborhood, to select one solution from the neighborhood and iterate. This is the key idea in single solution based metaheuristics, which are exploitation oriented based. They are more a classification algorithms than exploration. So as you know, the most popular techniques here are local search, taboo search, grasp, iterative local search, variable neighborhood search. So in this kind of algorithms, we try to improve a single solution. In population-based metaheuristics, we try to improve a population of solutions. So we are recombining solution to generate new solution, and we are replacing a whole population. So those algorithms are more exploration oriented. So you can have some direct recombination techniques that recombine solution directly, like evolution algorithms, particle swarm or scatter search. And you can have also some algorithms that do some indirect recombination, like ant colony, EDA, etc. So this slide is important. So if you ask me the question, what are the main involved ingredients of metaheuristics where we plug machine learning? So you will see that all my talk will be based on those ingredients. First, so this is an important slide. Why? Because I'm trying to give you a unified view. It doesn't matter which metaheuristic you can use, this will hold. So we can use some machine learning in the generation of the initial solution or the population solution. This is very important ingredient. In the objective function of the algorithm, of the problem. In the search operators, like in the neighborhood or in the combination or any operator dealing with classification, diversification. And of course in the parameters. As I told you, all metaheuristics have a lot of parameters. How to find the best parameters, and in offline or online. And here you can also use some machine learning to analyze the landscape of the problem, of the instance. You can use machine learning in decomposing the problem into sub-problems. And finally, this is very hot topic area, you can also use machine learning in the selection of the algorithms. Because if tomorrow you design, let's say, a portfolio of different algorithms, how to select the best one in real time, online or offline. Here also machine learning can be used in this task of selection of algorithms. So all my presentation will be based on those ingredients that you can find in any metaheuristic. So all the questions or the answers I will try to answer are dealing with those ingredients that we will find in any metaheuristic. Doesn't matter which one you will use. Okay, so I will give you some answers about those ingredients. So before, just a quick overview of what are the ingredients of machine learning that we will use. Of course, there are different tasks like classification, supervised learning, clustering, filter selection, or association rules. So those are the main tasks that we will use, and also reinforcement learning. And so I will try to answer the question of when we combine the metaheuristics with machine learning. It can be offline or online strategies. What is the aim of the hybridization, efficiency or effectiveness? And as I just present, what are the involved components? The search, parameters, the model, the problem, etc. Good. So let's start with initial solution, initial population. This is a very important issue. In general, those initial solution or initial population, the most commonly used techniques is random solution. Okay. But there are a lot of works that try to improve the way that we generate initial population. So there are three different techniques. The first one is we can incorporate in those initial population or initial solution some a priori knowledge. For instance, we can use good patterns in initial solution that has been learned from similar problems. In solving similar problems, past similar problems, you can try to use, for instance, some case-based reasoning and to find some good patterns that you will insert or you will plug in the initial solution. So the first idea is how to incorporate knowledge from past solving of the problems in the initial solution. The second way to use machine learning in the initial population is to fix in a smart way the initial solution position. As you know, diversification is a very important issue in optimization and in metaheuristics. If the population, the initial population, diversification of solution is a very important issue. So you can use, for instance, orthogonal experimental design to ensure that diversification of the population, initial population is very efficient. Okay? So I give you here just some papers, but the idea has been used in many papers. So the idea here is to fix the position of initial solution to ensure some quality in terms of diversification in the search space. And the third idea in the generation of the initial solutions is to how to use some machine learning to improve the initial solution. You can generate the initial solution in a random way or in orthogonal experimental design. You can use some learning techniques to improve the initial population. For instance, you can use some what we call opposition-based learning in the initialization of the population. You can use some interpolation techniques in statistics to this techniques is used in continuous optimization, and you can use also some techniques from neural networks to improve the initial population and start from, let's say, good quality initial population. So those are, let's say, some ideas in using some machine learning techniques in the generation of the initial solution of initial population. Let's switch now to the objective function. This is a very important issue in the last 2 years. It's a very hot topic area. The idea is that in many problems in engineering design or in black box optimization, the objective function is very, very expensive. You cannot use the original objective function in solving the problem. It can take just evaluation of one solution, it can take some hours, some days, and even some weeks. So if the objective function takes some weeks, you cannot use even any simple algorithm to solve the problem. So the idea is two different ideas here. The first idea is to approximate the objective function. How to replace the original objective function by, let's say, surrogate or meta model to reduce the complexity of the objective function. So here, of course, this is a very hot topic today, and there are a lot of techniques that have been used to answer this question. For instance, the linear regression models, LBF, decision tree, random forests, deep networks, Kriging, this is the most popular techniques, and deep Gaussian networks. So the idea is to, from a given set of points, to approximate the objective function and use this approximation, use this surrogate or this meta model in the metaheuristics instead of the original objective function. But another interesting idea is to reduce the number of evaluation. This is a very important issue. How to reduce the number of evaluation. So some techniques are using clustering. For instance, we cluster the solution and we use like a representative solution. We don't evaluate all the solution, but just some representative. But very interesting idea in the last 5 years that is very popular. It's what we call surrogate assisted optimization. So this is done online. I will give you some ideas about these techniques. So here I will give you an example how we can use metaheuristics using Kriging and expected improvement. Suppose that this is the original objective function, okay? But I don't know the original objective function. So the idea is to use very, very few solutions at the beginning. For instance, here I will use 4 solutions, okay? And from this, so the phase number 1 is initial surrogate building. So from the 4 points here, I will generate first surrogate model. Okay? For instance, if I use Kriging here, I will generate the red one. Okay? Now, I will use some indicators in this first surrogate, the expected improvement here. So I will construct the surrogate on those 4 points, and then the idea is to refine the surrogate with the metaheuristics. It means that I will select 1 point from this first surrogate. I will use, for instance, the expected improvement that try to find exploration, exploitation, compromise, and I will try to find the most promising point that I will evaluate using the original objective function. For instance here, this is the plot according to the expected improvement. So this point will be the best. Okay, I will try to compromise between the quality and diversification, and then I will evaluate the original objective function on this point. And then I will construct the next surrogate using 5 points, etc. So this idea is very interesting in terms of it's adaptive, it's assistant about the surrogate, and in time, I will converge towards the good regions of the search space. So I will not evaluate the objective function on non-interested regions. Okay? So this techniques, is very, very popular in the last days in solving complex problems in engineering design, like in automotive or aeronautics, etc. So we have a European project on those ideas, and we are trying to collaborate with some people from machine learning, some people from application in aerospace, automotive, and some people with high-performance computing, trying to bridge ideas from high-performance computing, machine learning, and optimization to solve very, very complex problems in aerospace. Good. Now, let's talk about the search operators. Any metaheuristics has some search operators to generate new solutions. For instance, the neighborhood concept or the combination operators concept. So here the idea is to use machine learning, for instance, to reduce the neighborhood. If you have a neighborhood which is very large, you cannot explore all the neighborhood. It's very time consuming. So the idea here is how to use machine learning to reduce the space that you will explore, and of course to make the search time more efficient. And another idea that I like is how to use machine learning in recombination operators. For instance, in crossover, as you know, crossover will recombine 2 solutions. The idea is how to extract some good patterns from the population of solution. You will extract what are the good patterns, using, for instance, association rules or decision tree. It doesn't matter which machine learning technique you are using, but the idea is how to extract patterns from good solution that you are generating and use those patterns in the recombination operators. So the crossover here will not be blind operator, but will use some knowledge in the generation of new solution. And this knowledge is extracted from good solution that you are generating. You will extract good patterns. Okay? For instance, here we have used some association rules techniques that generate good patterns from good solution, and you will use those models in the generation of new solution. So this is the main idea here. And of course, there are a lot of techniques, what I call non-Darwinian evolution algorithms. I don't know if you are familiar with this, with those algorithms like estimation distribution algorithms, or population-based incremental learning, or Bayesian-based optimization. Those techniques, the idea of those techniques, non-Darwinian evolution computation, is from the population, you will extract some, let's say, some probabilistic models or some learning models that characterize good solution, and from those models, you will generate new solutions. So you can use many, many different techniques like Bayesian optimization or some different learning or statistical learning models. So those algorithms are very popular in metaheuristics. Okay? So they are using machine learning to generate new solutions from good patterns extracted from the population. Of course, I don't have time, but you can also use some machine learning techniques in intensification or diversification tasks. If you would like to intensify the search or diversify the search, many techniques for machine learning have been used to answer those important tasks in machine learning, in metaheuristics. Good. This is also a hot topic in the last 10 years. And I imagine our colleague from the machine learning have the same problem. There are a lot of parameters. There are a lot of parameters in the generation, in the design of metaheuristics. There are a lot of parameters in the design of machine learning algorithms or models. So, and the efficiency of the algorithms are really sensitive to those parameters. You can do it offline. You can do it offline, means before the execution of the metaheuristics, you can try to use some statistical techniques or some machine learning techniques to find the best parameters. But you can also do it online. You can do it online during the search. According to the performance of different parameters, you will change the parameters online during the execution of the metaheuristics. So for instance, in single solution metaheuristics, some very important parameters like the size of the tabulist, the temperature in simulated annealing, or even the stopping criteria, or in population-based metaheuristics, the velocity in PSO, or the pheromone update in ant colonies, or the mutation probability, crossover probability in evolution algorithms, those parameters are very sensitive. The performance of the algorithms are very sensitive to those parameters. So here, there is a huge number of papers that deal with those questions, and the idea is to use machine learning to deal with this problem offline or online. But the most, let's say, to my point of view, interesting idea is to use reinforcement learning. Online, you can use some reinforcement learning techniques. So we have some nice paper that we have used the reinforcement learning in VNS. The idea of VNS is to have different neighborhoods. Suppose that you have a problem with different neighborhoods, okay? What is the best neighborhood that you will apply at a given iteration? In which order you will apply the neighborhood? Okay? Those questions are very important in VNS. So you can use some reinforcement learning techniques that help you to select the best neighborhood during given iteration. Okay? And of course, you can use this idea for the adaptive selection of any operators. If in evolutionary computation you have different mutation, you have different crossover, you have different search operators, what is the best at given step, for given instance, for given iteration? You can use some reinforcement learning techniques to deal with this important problem. Good. And this is also a very popular question more than 3 decades. This is, I think, the oldest way. How to learn about the landscape of the problem. How to learn about the knowledge. How you extract knowledge about your problem, about your instance. So here, the idea is to use machine learning to analyze or to extract the landscape of your problem. Okay? For instance, there are different indicators. You can generate the networks of local optima. How to extract the network of the local optima of your problem, to know more about your problem, to have knowledge about your problem. What is the multimodality of your problem? What are the variable correlation? What are the size of the basin of attraction? What are the plateaus and neutrality of your problem? So this knowledge about the landscape of your problem, believe me, will help you to solve more efficiently your problem. For instance, in the traveling celestial problem, we know that all the local optima are in given region of the search space, and they share minimum of 60% of the edges. We know that, okay? So those 60% fix them, and then concentrate the search in this region of the local optima. Don't do diversification. This is useless. So if you have some knowledge about your problem, we know that in scheduling problems, there are a lot of plateaus. It means that many solutions have the same quality. This is not good for metaheuristics. If your search space has many plateaus, it means that the search is very blind. You cannot design some smart metaheuristics. So you have to change the landscape. You have to change your objective function to discriminate those solutions. Because if you have landscape where you have many solutions with the same quality, this is not good for any metaheuristic. Okay. So a lot of works in this area. And this is also one of my main concerns in the future. We are interested in big problems. And in big problems, decomposition is very, very important. Okay? So decomposition of the decision space, it means that how you decompose the problem, fixing some variables, for instance, and then doing the search only on the other set of variables. Here you can use, for instance, some filter selection techniques, some statistical techniques to which variable you have to fix. What is the decomposition, the most efficient decomposition. In many objective optimization, in multi-criteria optimization, you can also do some decomposition in the objective space. If you have many criteria, it's not efficient to solve the problem, so you have to decompose the problem in the objective space and not in the decision space. And finally, you can also have some decomposition in data space. For instance, if I give you the vehicle routing problem, if you have millions of clients, or in location problems, or routing problems, even scheduling problems, if you have millions of clients, you have to do some decomposition in the data space. So here you can do, for instance, some clustering. If you do some clustering, you will decompose your problem into many subproblems and then solve the problem for each subproblem and then aggregate the results. So this idea of decomposition, I think this is my point of view, will be very important in the next decade to solve big problems. And a lot of ideas of machine learning to help you to find the best decomposition. Decision space, objective space, and data space. And finally, you can also do some decomposition in the output. I don't know if you are familiar with multi-objective or multi-criteria optimization. In multi-criteria optimization, the output is a set of solutions. Is Python front, is non-dominated solution. But in many problems, this set is huge. You have to do some machine learning from this output to extract knowledge. For instance, do some clustering, do some learning from this output to select some solution from this output. So this is a nice idea, how to learn the output of optimization technique, to do some deduction, to select some solution, etc. So this is also a hot topic in multi-criteria optimization. How to use machine learning to analyze the output of the algorithm. Good. And this is, I think, one of the next interesting questions for the future, how to use machine learning to select the best algorithms. Imagine tomorrow that you have like portfolio of algorithms for a given problem. How to select at a given time, offline or online, the best algorithm for your problem. And here, for instance, those ideas has been used in hyperheuristics and here many techniques have been used to solve this well-known problem. It's more general problem about algorithm selection. Okay? You can use some reinforcement learning, some deep learning techniques to select online the best algorithms. And you can even use some ideas to automatically generate the heuristics. Tomorrow, we can automatically generate the best heuristic for a given problem. If you have some, let's say, the main ingredient, you have the main ingredient, how you automatically generate the program. You can use some ideas from genetic programming. Genetic programming to generate the best, automatically, the best algorithm for your problem. Good. So, to conclude this first part, how machine learning can help metaheuristics, let's say my point of view is that in the future machine learning is a must. It's not an option. You have to use those techniques to design more efficient and more effective metaheuristics. It's very important to guide the design of efficient techniques according to the knowledge offline or online, but be careful. You have to take into account the trade-off between the benefits and the additional cost of learning. So I'm sure that if tomorrow you are submitting a paper about research in this area, they will always ask you, yes, it's good, it's nice, but what's about the cost you are adding you are adding in machine learning. Excuse me. Okay? I think one of the participants is calling me. Okay, so this is good. Switch to the second part. So I will conclude this first part. There are a lot of promising research issues. A lot of promising. Of course, we are using some deep Gaussian networks in this assisted surrogate optimization. Those ideas, I am focusing here on metaheuristics, but those ideas can be used in mathematical programming, in exact algorithms. Okay? For instance, how you use machine learning in branch and bound to do the node selection. Okay? Instead of doing it deterministic way, you can use some machine learning in interval programming, in Monte-Carlo research. Those are more deterministic or random techniques. Why don't add some knowledge into the generation of intervals, or the generation, if you would like to do it in non-exhaustive way, in the Monte Carlo research. So those ideas, this is my point of view, can be also used in exact optimization. And of course, tomorrow, how to deal with multi-objective optimization, how to deal with multi-level optimization problems, bi-level optimization, in solving, in using metaheuristic to solve this kind of problems. If you have some dynamic, I didn't focus on dynamic optimization, but in machine learning is a must. If you have dynamic problem, if you have dynamic optimization problem, how to use machine learning to predict the future. Okay? Because in dynamic optimization, you have dynamic event. For instance, in vehicle routing problem, a new demand. But if you have historical data, you can predict. Don't do it in blind way, but use the knowledge from the past to predict which part of the space the new demand will be. Okay? So in dynamic optimization, there's a huge work in the future in using machine learning to solve those problems more efficient way. And the software aspect is very important. How to couple the software in optimization with some machine learning libraries. This is an issue. This is a very important issue. And of course, we are very interested in parallel implementation of those ideas. High-performance computing, like using multi-GPUs, multi-core systems, or even some cloud computing, is a very important issue in this area. If you would like tomorrow to solve big problems, you are adding here some complexity, so you have to think to design parallel algorithms, to solve those parallel algorithms in efficient way on those very popular architectures. And they are not costly, okay? For $200 you have GPUs. Good. Okay, so now let's switch to how metaheuristics can help machine learning. This is another topic. And you will see that, let's ask this very important question. What are the main issues in machine learning? This is my point of view. The main issue in machine learning, those three questions, at least from my point of view. The model representation. So in any machine learning algorithms, you represent the model, the structure or the functional form of the knowledge. It can be a partition, it can be a tree, it can be a network. This is what I call the structure of the model, the representation of the model. Good. The second issue in machine learning, the objective function, the scoring function. This is really the main issue. How you measure the quality of the solution. From my point of view, the objective function is a very important issue. And finally, you have the representation. You have the objective function. This is the search space. The third question, how you will find the best model in this search space. What is the strategy to use to explore this search space defined by the representation and the objective function to find the optimal or good solution? Those are the main issue in any machine learning technique. Good. my point of view too, this has been an interesting point of view because this is a view from metaheuristic or optimization researcher. Many, you will see that this is very strange, but if you analyze the popular algorithms, many algorithms are very simple metaheuristics from our point of view. I will try to show you that. So if you go towards the machine learning algorithms, you will see that they can be seen as basic metaheuristics. Many of them, local search, grading techniques, are the most popular techniques in machine learning. And believe me, there are many new opportunities for metaheuristics to solve such big problems. I will try to convince you. Good. Let's start with clustering. The good news, all those problems are NP-hard problems. All the problems I will talk about are NP-hard optimization problems. What does it mean? It means that all machine learning algorithms that are using their approximation, none of them is exact algorithm. I'm talking about the popular one. Okay? So you have to know that. All our machine learning algorithms that you are using every day are just approximation, are just heuristics. Let's talk, for instance, about the partitioning methods or hierarchical methods in clustering. The k-mean, the k-median, those are basic local search algorithms. Basic local search. It means that, what is the objective function? The issue is the objective function. You will use some similarity measures, but there are different objective functions. The issue, what is your objective function? Then, I try to convince you that the questions are the same. What is the initial solution, for instance, is the k-mean? This is a very important issue. How to select the centers, how to select the representative. My point of view, this is the issue of the initial solution. How to fix the initial solution. How you represent your cluster. This is very important issue in metaheuristics. There are a lot of symmetry problems. If you have bad representation here, I can tell you that stop to design any metaheuristic. What are the neighborhoods you are using in the heuristic? And if you analyze things like, from this point of view, the conclusion is that the most popular algorithms in machine learning are simple, very simple heuristics. So the idea, for many researchers, there are a lot of papers that they are trying to improve those basic heuristics to design more advanced heuristics, metaheuristics to solve those complex problems from the objective function point of view, from the initial solution, from the representation of solution, from the neighborhood, from the combination operators. Those are the most important issues. So there are thousands of papers dealing with that. Good. So, as you see here, in partitioning algorithms, most of them are local search, basic local search. The nice issue is that if you go towards hierarchical methods or even decision tree, you will find that the algorithms are very basic greedy algorithms. The most basic that you can find. Greedy algorithms. So, for instance, in decision trees, what is the representation? Is a tree, okay? How you construct, you build the tree, the algorithms are very basic, greedy algorithms. And the idea is, the most important question, which node you will select at the beginning. So you can use some Gini index, entropy, gain. Those are heuristic. They are trying to find what is the best greedy way to do the partitioning and to select the attributes. Good. So if you answer those questions, you will find that all those algorithms are simple, greedy algorithms. Very simple greedy algorithms. And I will try to show you that just changing these greedy algorithms to random greedy algorithms, you will design random forest. What is random forest? What is the idea of random forest? This is well known in our community. If you take a greedy algorithms, its complexity is simple complexity, but the problem is that the choice at the beginning will influence the final solution. it's very sensitive. The greedy algorithms are very sensitive to the decision at the beginning. What is the idea for the first? Very simple idea. The idea is to answer this drawback of greedy algorithms is just to select some, to do some selection of the variables at the beginning that makes greedy algorithms more generate different trees. You will generate different trees according to different features at the beginning. Just for me, it's like a randomized greedy heuristic. It's a randomized greedy heuristic, and the randomization is done according to the selection of the features at the beginning. And then you will select different trees, and you do some majority voting, just to show you that it's not, let's say, a revolution. It's a simple idea, but it shows the efficiency in practice. Just to answer. So I think, what is my message? My message is to analyze those machine learning algorithms from the optimization point of view. It helps you to improve those algorithms. It helps you to improve those algorithms. And of course, the problem here is the trade-off between the bias and the variance. And you can also use some multi-objective. This is another nice idea. Another nice idea is to do some multi-objective formulation of the problem, because there is some bias, trade-off between bias and variance. So for instance, you minimize the error and you minimize the tree size of the problem. So my other message is that doing some multi-objective formulation of some machine learning, it can help to solve better the problem. Good. In SVM, the main problem in SVM, the main issue in SVM are optimization problems. As you know, in SVM, the issue is to maximize the margin around the separating the hyperplane, okay? So the idea is to generate the support vectors and to maximize this margin, okay? And if you are using some linear SVM, the problem to solve here is quadratic optimization problem, but still with linear constants, okay? But if you are using some non-linear SVM, some kernel functions which are not linear, here you will generate very complex optimization problems. And those complex optimization problems, you can use metaheuristic to solve those problems because they are NP-hard, they are difficult problems. So you have to design some approximation to solve this problem. So there are a lot of issues in support vector machine that the main issue is an optimization problem. Good. Yes. Yesterday we had a nice talk about deep learning, CNN, neural networks. Let's just talk about neural networks. In neural networks, there are a lot of optimization problems if you would like to automatically design the best suited neural network for your problem. For instance, in just simple neural network, what is the best architecture of the neural network? This problem can be formulated as an optimization problem. Of course, it's NP-hard, but it's better to solve it using automatic way than better, I don't know, but it's then manual way or knowledge from the decision maker. It would be nice to formulate this problem as an optimization problem and try to find the best tuning for your network. And of course, for deep networks, it's much more complicated. I have a new problem. We are working on that, formulating some problems, optimization problem for deep networks. We generate problem with 4 million variables. So suppose that you have to solve a problem with 4 million variables. You have to design new techniques. So this is why I'm talking about decomposition. So we are starting a new PhD on this issue, how to automatically design the best suited deep network for your application, but you are generating very big problems that no one can solve today. 4 million variables. Okay? And I asked a question yesterday. People from the network are using backpropagation based on gradient. Gradient is simple local search. And they are happy with that. It's simple local search algorithm. Why they are happy with that? Many reasons. But this is a very interesting question. Why in this community they are happy with simple local search to train the network? You have to think about this question. There are different answers, but still interesting question. Good. Feature selection. Feature selection, if you are using a wrapper approach, not a filter. Filter approach, that feature selection means that you will select some variables according to a set of variables, okay? If you can do feature selection, then classification, then evaluate the model. This is from the optimization point of view not interesting. People here are using greedy algorithms. They are using simple greedy algorithms according to some criteria. But the wrapper approach is more interesting. It means that you do the feature selection, you do your classification, you evaluate the model, and change the feature selection. This problem can be formulated as an objective optimization problem. NP-hard problem. What are the best features for my classification? What is the objective function here? The objective function is very costly. The objective function you have to learn to evaluate your model. It's very costly. And you can use this idea about surrogates at the beginning. You can use this idea about surrogate to approximate this complex objective function. And then, what are your objectives? Of course, the test error, the number of attributes. But this problem is NP-hard optimization problems. Objective function is very costly. So you can use different ideas from surrogate-assisted optimization to solve this problem. Okay? So any metaheuristics can be used, and some ideas from surrogate-assisted optimization can be used. I will speed up here. Association rule mining. The best known algorithm here is a priori. A priori, the idea of a priori algorithm, why it's efficient? Because it's using the support of a rule to reduce the search space. But if tomorrow, we have some work on that. If tomorrow you have other quality, of the rules, why the support and the confidence? For some problems, the support is not good quality. You have to find some rules that are not well supported, but rare rules. So if you change objectives, those efficient algorithms cannot be used. Because this efficiency, we will lose this efficiency. And here we can even have some you have different qualities here. The conviction, the lift, the surprise, the length, the number of rules, diversity of rules. So if you add some other objectives for your problem, you will lose some properties. This property, you will lose it. The down closure property in association rule, you will lose it. And here you will have very complex optimization problems. And even you can even have some multi-objective problem. And any multi-objective metaheuristics is welcome to solve this complex problem. Okay? So even in association rules, the idea of designing metaheuristics to solve this problem can be a must for some formulation. For some formulation. Not for lots of formulation. This is for me a very hot topic. Very, very hot topic. In any machine learning task, the hyperparameters of the models. In any model, you have a lot of parameters. How people are fixing those parameters. For instance, and those parameters can significantly impact the performance of the machine learning model. It occurs everywhere, supervised and unsupervised. For instance, in SVM, if you are using some kernel hyperparameters, there are many parameters in the kernels. How to find the best parameters? In artificial neural networks, there are a lot of parameters. How to find the best parameters? We can formulate this problem as an optimization problem. It's an optimization. This is the formulation. You have a learning algorithm. You have a set of parameters. You have a training set, test set. You have a model which depends on the training set, on the parameters. You have to optimize this loss function to assess the quality of the model using the test data. This is an optimization problem. Of course, it's a complex problem, but you have to solve it. Don't do it manually. It's better than do it in manual way. So, for some machine learning model, this problem is very, very complex. I told you, for instance, in deep networks, you have millions of variables in this problem. Those problems, I think that a lot of work is still to do in this area. This is my point of view. So the manual tuning leads to poor performance, even if you have knowledge. I prefer to do it automatic way. So metaheuristics, I'm here to defend metaheuristics, of course, are good candidates. They are good candidates. You have very complex problems, NP-hard problems, big problems. Metaheuristics are good candidates. Good. What are the challenges in this area, in this hyperparameter? You have very expensive objective function. Very expensive objective function. The objective function is the learning of all the model. It's very expensive. So, you can use this idea of surrogates, of meta-models, to reduce this complexity. You have uncertainty, a lot of uncertainty. If you change the data set, or the learning or the test set, the objective function will be different. So how to deal with this uncertainty in the formulation? Multiple evaluation of the objective function gives you multiple results. If you change the data set, then the quality will change. So how to deal with uncertainty in this problem? Those are very hot topics in optimization. And complexity, of course. You have very big mix of problems, integers, discrete, continuous optimization, many constraints in the domain constraints, combinatorial exposure, so you generate complex, big, mixed problems. Those are the challenges in the hyperparameters in machine learning. So, let's conclude this part, metaheuristics for machine learning. Machine learning problems are NP-hard problems. Objective function formulation is a very important issue in this area. Many state-of-the-art machine learning algorithms can be viewed as simple metaheuristics, and metaheuristics are very good candidates for this really critical issue, the hyperparameters, automatic finding the hyperparameters or anymore. Now, the perspectives for metaheuristics for machine learning, I think that it will be nice. I hope that you are convinced that there is some place to design more advanced metaheuristics for some machine learning problems. There are some places, there are still some work to do here. There are some interesting work how to formulate some machine learning problems are as multi-objective and even bi-level problems. I saw many papers trying to formulate the clustering problem as bi-level problem. There is still some work to do here. Of course, the parallel aspect, the parallel design of algorithms is a very important issue. And of course, how to combine those NP-hard problems, but there are many ideas to combine metaheuristics with some mathematical programming or some exact algorithms, at least for some sub-problems to solve those issues. And as I told you, the uncertainty, how to deal with the uncertainty in this problem, the objective function or the data set, and there is a lot of things to do in this surrogate assistant for hyperparameter optimization in machine learning techniques. And of course, I will end with some publicity. So in October, at the end of this year, we will organize the 7th edition of Meta Conference. So Meta Conference is metaheuristics conference, but people from machine learning are welcome to bridge the gap between metaheuristics and machine learning. So I just extended the deadline just for you. Don't tell it to other people, but just for you, we just extend the submission deadline. So there are different types of submission. There's short paper, long paper submission, or papers will be in the Springer book proceeding, and we have 2 special issues. One special issue, interesting special issue in this journal, International Transaction on Terrestrial Research, Mesh Optimization and Learning. The special issue here is exactly what we are talking about today, bridging the gap between optimization and machine learning. We have a special issue here only on this topic. So this is why you are welcome to participate to this event. In a nice place, of course. Rabat also is a nice place. Any question?
Thank you very much.
Good morning. Thank you for your presentation. I'm Hajar Moulay, and I'm a PhD student in artificial intelligence. My first question is about parameter tuning. You have said that we can use either online or offline parameter tuning. In your opinion, what is better, online or offline?
If you have an answer for this question, I will not talk about it. So, my experience, I will tell you the drawback and advantage. We cannot give you an answer. It depends on your problem, but I will give you my concern. In offline optimization, you are doing only one time before. So the advantage is that complexity is offline, so you do it once. Good. But the idea of online is much more efficient but more complex. I will give you some concern here. If you are using, for instance, any neighborhood or any search operator, if you have many search operators, the efficiency of those operators do not depend only on the length, on the input of your problem. Depends on at which the time of the metaheuristics. At the beginning, some operators are better than others. At the end, some other operators are better. So this is why online is more adaptive techniques. So you can use some reinforcement learning to adapt in real time between different operators. So it's more complex. You will add higher cost. So you have to convince people that this cost that you add is give you more efficient. But for some issue, online is better. But for some other issue, like my point of view, if you are dealing with mutation rate or crossover rate, do it offline. But if you are dealing with neighborhoods, you are dealing with different combinations, do it online. Because this adaptive way to manage operators is better to do it online. But for some parameters, do it offline. The size of the population, things like this, do it offline. So the answer is, depends on which parameters and also the benefits that you will take it in managing this online.
Thank you. My second question is about problem decomposition. You said big problems. What do you mean by big problems? Is it about the data size, the size of the data set, or the size of the search space?
Not only I can give you some problems which are very easy to solve even with big data size. For me, it's not only the size of the problem, it's the structure of the problem. I can give you some problems with not important size, but very difficult. And I can give you some problems with very important size and very easy to solve. So what I mean by big is not only the size of the problem, but the complexity and the structure of the problem. Okay? So, an example. This big problem with one. Let's talk about continuous optimization. In continuous optimization, 20 years ago, the size of 50 is big. Now, if you take state-of-the-art papers, 100, 200, 1,000, it's very big for that. It depends on the community too. But now, in 10 years, millions will be the issue. So it depends on the community which kind of discrete combinatorial
resources that we have.
And things are evolving. So I can ask you the same question. What do you mean by big data? You know?
Thank you.
Thank you for your presentation. My question is about the use of machine learning in the algorithm selection or tuning for different engineering problems. We have tried to use, for example, algorithms such as neural network SVMs, but the problem is with the data set. Because for most problems, there are not that data set which contains, for example, variables or features, attributes, except for some few problems that the majority of problems, for example, in aerospace, VRP, the variables features are not yet defined for such problem. If you have a recommendation, the variables for this problem, for example, are not yet defined. That's what I have seen.
I was 2 weeks ago in Chile, far from here,
yes.
And they asked me exactly the same question, exactly the same question. Very interesting question. For many problems, indeed, you don't have even the features.
Yes.
You don't have even the features. If you don't have the features, how you do some machine learning? Still a lot of work to do. It depends on the problem, but you are right. For many problems, defining the features is still a complex problem.
Yes.
But it depends. Yeah, you are right. You are right. So we are far from. There are a lot of work still to do in this way. To find the best features for given problem, to learn about it.
Thank you, sir. Thank you for this presentation. So my question is how we can use machine learning for choosing the best meta-heuristic. Can you give us some example?
It's really easy. I can one example. A lot of papers dealing with that, but I like this idea. Is you can formulate this problem as I like formulation, so I will talk more on formulation. What is this idea about? It's in the first one. Okay, so yeah. Suppose that you have a portfolio of algorithms. Okay, you have a set of algorithms. This problem is well known even in other communities. So let's talk about selection of algorithms. Okay, but do it online, huh? Online. So you can formulate this problem as a sequential learning algorithm. You can use any reinforcement learning technique to select at a given time. So you apply different algorithms and then you select the best one using reinforcement learning. So this problem can be formulated as a sequential learning problem. And then you can use any reinforcement learning technique to solve this problem. So this problem is much more than the meta-heuristic selection. It can be formulated for any algorithm selection for a given problem. And you can formulate it as sequential learning problem using reinforcement learning. No, you have to apply the algorithm. It's in sequential learning. You start. What is the difference between sequential learning and classical learning? At the beginning, you don't have knowledge. You don't have knowledge. You don't have data set. You have nothing, and you do it in a sequential way. You apply the algorithms, and from the output, you select the best one. This is the idea of sequential learning. You will learn in sequential way. You apply the algorithms. You see what happens. You select. But you start from nothing. This is the interest of sequential learning. You don't have data sets. Sorry?
What's secret to have a good result in your optimization? Because you use the probabilistic approximation.
Well, this is another question. The question is not security. The idea is what is the quality of the approximation. This is the question of, no, in meta-heuristics we are dealing with approximation algorithms. I don't have the proof to find the optimal solution. It's NP-hard problem. This is your question? So, We are dealing with complex empirical problems. Okay? We cannot design polynomial algorithms that give you an optimal solution. So in this kind of algorithms, you don't have any guarantee to find optimal solution. And any machine learning algorithms, you don't have the guarantee to find optimal solution. If someone tells you you have the optimal solution, he's a liar. Okay? You don't have even no way to have the guarantee of the optimal solution for those problems.
Congratulations by your talks. I would like to go back to the question yesterday and the convolutional neural networks. In the history, we can find a lot of evolutionary neural network models, particularly with evolutionary algorithms, difference. But now, I agree with you, people is using stochastic gradient. Of course, there is a local share, but it is really to manage thousands and even millions of weights. The convergence is good. What is we are now trying to, with some students, to thinking about the possibility to use differential evolution and other techniques. In fact, the winners in the last competition, in the evolutionary competition conference, are differential evolution algorithms. But really, in the competition, people are using 1,000 of variables. In large scale, 2,000 of variables. But when we are discussing about CNN, the number of weights is tremendous. Then we are trying now to start with this, but I am not sure about the future in the use of now evolutionary algorithms or any other kind of algorithms. What is your opinion for the future of that?
We all agree that it's a very challenging question. I agree with your comment. I think my point of view here, I will tell you the history. I have one colleague working for a huge company that are using deep networks for some strategic problems, and they are doing manual tuning of the network, and also they are using classical algorithms for the learning. And this partner knows very well the optimization metaheuristics, and we just defined this challenge. But at this time, I learned some papers from this stochastic gradient, etc. The answer I find is that they analyze the landscape of the problem, and they found that this is important to analyze the landscape. And they found that the quality of the local optima in this landscape are okay, are good. So if you have optimization problem where the local optima are many local optima, okay, but the quality of the local optima is good, you don't need sophisticated algorithms that escape from those local optima, etc. We are okay, because this is why those people are happy with that. But still, I think that is a challenge. It's challenging, it's challenging, risky, very risky challenge to start to see what can we do in this to improve those algorithms. But it's very risky. It's risky, but it's a nice challenge, Yes. High risk, but let's see what can be done. We can learn from that. If it doesn't work, we will see why it doesn't work. But there are we agree, very few research issue in this. This is important.
Another question? One more?
Yeah.
Okay, thank you for a very energetic presentation. Right. My question is that how do we compare the performance of different algorithms if in the case that we don't have any benchmark?
For which problem we don't have benchmark?
Any problem, let's say.
If you don't have benchmark?
Yeah, we don't have any benchmark. How do we compare the performance of the algorithm?
Of metaheuristics algorithms?
Yes.
I will give another keynote for answering this question.
Any suggestion?
Yeah, it's very cool. I need a lot of time to answer this question. Comparing algorithms, it's a very complex issue, but I have answers that it depends on your problem. If you have benchmark, no benchmark, if you have the optimal solution, a good lower bound, upper bound, it depends. If you have practical problem, the industry will tell you, this is my solution. If you do better than this, you will have the money. That's all.
Is it accepted if we compare with only with the empirical data?
You know, all machine learning task works from data sets. If you don't have data sets, how you can perform the application? But so in this area, how we do performance depends. Some problems have some benchmark. Okay, if you're working on real application, you have some real instances. But I can just add something. What I don't like for many problems, they are generating random instances, uniformly generated. I don't like this. Why? Because what I say, real life is not random. You know? Real life is not random. You can have some surprises. If you are using some random instances and evaluate algorithms, tomorrow if you have a real instance, you will have surprises. The performance will not be the same. So this is a key issue. Your question is very interesting. Be careful in the selection of the batch. You can have surprises.
Last question, please.
Hi, thank you for.
No, better now. Thank you for your presentation. I think it's a very interesting topic. I was wondering about a question in the same line that Francisco Herrera just asked you a few moments ago, because as we go higher and higher in dimensionality, the ability of differentiate or to distinguish between solutions becomes harder, because if you have a very, very high dimensionality, everything is different. So how are we going to cope with that in metaheuristics when we need to differentiate solutions? We can do that in high-dimensional problem, which is the future right now.
Nice question. If you have an answer today, it would be nice, but this is, believe me, it's my concern for the future. Just starting with book. I can tell you the same issue. I have some more, or we have some work on multi-objective optimization, and some people are talking many objective problem, many objective. And if you're formulating the problem as many objective, all solutions are priority solutions.
Yeah,
everything is good.
Everything is in the initial Pareto, and you can go further.
Exactly. You know, it's a very interesting question, but what I'm talking today is just, I think that still something to analyze those kind of questions and answers to. But I'm okay with you. It's like big number theorem, you know. If you have big instances, perhaps all locality are a good solution.
Do more and more, for example, try to find the best set of features, and you have out of them or many hyperparameters, and your metaheuristics start to stagnate.
What is okay? What we are okay with that still some place to do in this way. But of course, it's a very risky issue. But we have to do something to answer those kind of questions. But of course, as I told you yesterday, people that are happy with that, it means that it works.
Let me know another question, only to know your opinion. What is your opinion? Now, when we check the literature, we find a lot of new methodistics, basically very inspired. I have one experience now. I have 80 students in my course. I propose to my students, it is incredible, an alternative exercise. You can choose a new methodistic to study it and to avoid the exam. All my students prefer to study new methodistic. But it's crazy. What do you think? What is your opinion about this?
My opinion is categorical. This, you know, I like this book, and one keyword that is important for me, the most important keyword is unification, unified. So, in my book, let me answer this question. I can tell you something. You can take two different metaheuristics with different names, completely different names. You will have look inside, they are the same. The same. And be careful. You can take two algorithms with the same name, and they are completely different. So be careful. Today, as you see, when I'm doing this lecture about metaheuristics, the first thing I am telling my students, forget the names. Don't talk about names. Talk about the search component of metaheuristic. I have the list on this different search component. And then what is important issue for me, what are your answers for those questions? So for those people creating new things, I will ask them, did you have something new for answering those questions? If the answer is no, in the trash. If the answer is yes, convince me that you have something efficient in neighborhood, in a combination, in a classification, in definition of the objective function, initial solution. So, as I told you, let's unify this word and ask the most important question. In this slide, the names, forget. So there's something new perhaps for some, but 90%, it's like changing names.
Yes, I think so. Basically, the idea is the same. Any mathematical operation to combine two solutions, but finally the mechanism is more or less the same.
I will tell you something. Look, many papers in making PSO, discrete PSO. You will look at it, it's evolutionary.
We can continue it after...
Yeah, but it's...
yeah. Very good. Thank you very much, thank you very much also for Paco. Now we have a break coffee after there is the final station. Okay, thank you very much.
un poco de